And at last, it is time to enter Chapter 13, the final chapter of Pre-Calculus Made Difficult. This chapter is a bit of a hodgepodge, as its name, identities, inverses, equations, might suggest. And today, we'll be concentrating on identities. Now, you have met lots of trig identities already. These include statements like tangent of theta is sine theta over cosine theta, or the Pythagorean identity. And you've seen how identities beget new identities. For example, if we take the Pythagorean identity and divide both sides by cosine squared, and use this first identity, that sine over cosine is tangent, we get this alternate Pythagorean identity. 1 plus tangent squared is secant squared. These are identities because they hold for all values of theta for which these expressions are defined. You've seen things like cofunction identities, which explain why cosine is called cosine. Cosine of an angle is the sine of that angle's complement. Same story for cotangent and cosecant. You've also encountered the sorts of identities that I referred to as on-the-fly identities in these videos. For example, in the previous video, we used the fact that sine of theta minus pi is minus sine of theta for any theta. And this was the kind of identity that I said you don't memorize. You just read it off the unit circle if you need it. There's theta. So if I come across the expression sine of theta minus pi, I might say, okay, theta. Then I have to subtract off pi. That gives me a half turn going the opposite direction, which takes me to this point. The sine of theta minus pi is the y coordinate of that point. Well, clearly that's equal but opposite to the y coordinate of this point, which is sine theta, which is why I get that negative. The two expressions, sine theta and sine theta minus pi, have the same magnitude, but opposite signs. Algebraic signs, SIGN. What are some other identities we've met? Oh, I know. What do we know about cosine of minus theta? Well, we know that that is always the same thing as cosine of theta, because cosine is an even function. It absorbs that negative. That's a kind of identity. And similarly, we know that sine is an odd function, which means that a negative in that position gets pulled through the sign. So these are all identities that we have either firmly lodged in our mind, or, in the case of this one or others like it, we can derive on the fly in a few seconds just by thinking about the unit circle. But there are more. Oh yes, there are more, including a few more that you should know. The main ones we will discuss today are the sum identities for sine and cosine, and the double angle identities. We will have to fight a little bit to come up with the sum identities. Once we have them, though, we will be able to use them to derive the double angle identities in a matter of seconds. And as I said before, identities beget identities. I will show you, beyond that, how we can use the double angle identity for cosine combined with everybody's favorite identity, the Pythagorean identity, to then derive what I call the square killer identities, which in turn can be massaged into another form called the half angle identities. But our main focus will be on these two, the sum and double angle identities for sine and cosine. Those are the ones your calculus teacher, when you get there, will expect you to know, especially the double angle identities. But to get to those, we need to begin with the sum identities. All right, so what are these things? Let's start with the sum identity for sine. This is going to be an identity that gives us a way of expanding the expression sine of alpha plus beta. Now, there's always somebody. It's not you, but it's somebody sitting in the class with you. There's always somebody who thinks that everything distributes over addition. So that person might think, well, can't I just say that sine of alpha plus beta is sine of alpha plus sine of beta? No, 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 1,000 times no. In fact, here's a quick counterexample. What's sine of 60 degrees plus 30 degrees? Well, of course, that's sine of 90 degrees. And thinking about the unit circle tells us that sine of 90 degrees is the y-coordinate of that point, which is 1. Is that the same thing as sine of 60 plus sine of 30? No, it is not, because sine of 60, everyone knows, is root 3 over 2, and sine of 30, everyone knows, is half, and root 3 plus 1 over 2 is definitely not equal to 1. So we've seen a specific example where sine of alpha plus beta is not the same thing as sine of alpha plus sine of beta. Okay, but then you'll wonder, well, what is it then? Is there a way I can expand sine of the quantity alpha plus beta? What would it look like? Well, I will show you a very clever derivation of it. And the derivation is going to depend on something that occurred at the end of chapter 11, which I didn't cover in these videos, but it's so quick that I can do it in a few seconds here. So let me rope off a little room. I'm going to use what in the book I refer to as the SAS Area Formula. Given a triangle, we all know that if we know its base b and its height h, that the area is half the base times the height. We discussed that in the very first video in this trigonometry series. But in chapter 11, we came up with two other formulas for a triangle's area. The first of which, the simpler one, was this SAS area formula. I called it that because instead of getting the area in terms of base and height, we get the area in terms of any two sides and their included angle. Side, angle, side. Of course, we know that side, angle, side is enough to determine a triangle, so we should be able to come up with an expression for a triangle's area in terms of those three pieces of information. And in fact, this is very easy. To find the area in terms of the two sides and their included angle, we just rely on the formula that everybody knows already. The area of any triangle is half its base times its height. And in this case, if we take the base to be b, we get half of b times the height. But the height isn't given to us. No matter, we can find it anyway. We drop this perpendicular and we look at this little right triangle that we've created. We know its hypotenuse is a and this acute angle is theta. So the height, the side opposite theta, is of course, by our SOHCAHTOA shortcuts, a sine theta. So since that's our height, we find that the area is half of b times a sine theta. And I like everything to be in alphabetical order, so I'm going to turn those two factors around. Half ab sine theta. Well, look what we've done. We have the area of our triangle in terms of the two sides and their included angle. Aha! We win! I told you it was easy. And it's a handy little formula because now, for example, if we have a triangle, two of whose sides are, say, 4 and 6, and the angle between those sides is, say, 38 degrees, well, we can very quickly conclude that the triangle's area is what? Well, according to this new formula, it's half the product of the sides times the sine of their included angle. Well, the product of the sides is 24, half of that is 12, and we just have to multiply by the sine of 38 degrees. And then, of course, if you want to approximate that, your calculator will tell you that it is approximately 7.39 square units. So the SAS, side angle side area formula, tells us that any triangle's area is half the product of any two sides and the sine of the angle between them. As I said before, it's a useful little fact. It turns out to be helpful in surprising places. Actually, before I let this go and get back to our sum identity, I want to meet a possible objection. Someone might have looked at our derivation of this formula and said, well, that's fine, but what if this angle had been obtuse? Then it's not clear that the derivation would still work. Fear not, it still works, and I want to take a second to demonstrate that it still works. There's just one little twist. If this was our triangle, and we were trying to come up with our side angle side area formula, so in terms of a, b, and theta, well, of course, we'd begin the same way. We'd say it's half the base, which is b, times the triangle's height. But where's the height? Well, if b is our base, when we drop this perpendicular, of course, it falls outside of the triangle. The length of that perpendicular is the height we want. But what is that? When we had an acute angle, it was easy, because then we could say, oh, I have a right triangle, I know the hypotenuse, I know this angle, that side is opposite it, so of course it's a sine theta. But that's not what we have over here. Theta does not lie inside of this right triangle. Well, that's no problem at all, because I know what that acute angle is that is next to theta. That angle is the so-called supplement of theta. It's pi minus theta. 180 degrees minus theta. Well, now it's easy, because now in this right triangle, I know the hypotenuse A, I know this acute angle, pi minus theta, so that means this leg of the triangle, opposite that angle, which is indeed the height I want, is going to be a times sine of pi minus theta. That's the height, so I can pop that into my formula. Hey, but wait a second. This isn't what we had before. This says that the area of the triangle is the product of the two sides, A and B, and the sine of the supplement of the angle. I thought it's supposed to just be the sine of the angle. That's what it says right here after all. But don't worry. Don't worry. Think of this expression, sine of pi minus theta. What are we doing in this section of the book and in this video? We're talking about identities. Hey, sine of pi minus theta. That's something I can get by thinking about the unit circle. That's one of those on-the-fly identities that I probably don't know off the top of my head, but I can get it in about 2 seconds, because whatever angle theta someone might throw at me, pi minus theta, what's that? Well, angle pi is a half turn. If I'm then subtracting off theta, this angle, that would take me to a point right here. So the sine of pi minus theta, that's the y-coordinate of that point. But clearly, that's the same as the y-coordinate of this point, which is the sine of plain old theta. So I can see from the unit circle that sine of pi minus theta is sine of theta. So that means up here, I could replace that thing, sine of pi minus theta, by plain old sine of theta, thanks to this helpful identity. And now I see that yes, even in this case where I have an obtuse triangle, the area is still half the product of any two sides times the sine of the angle between them. So this statement, as I've expressed it rhetorically, still holds. And it always holds for any triangle, any two sides, and their included angle. Good. Let's move this out of the way. And finally, let's start talking about this sum identity. This may have seemed like a weird digression about area, but very interestingly, I can use it to come up with a sum identity for sine. Watch this. I think you'll like it. Let's start with this vertical line segment of length 1. First, let's think about the line perpendicular to it. And now, given angles alpha and beta, what I'm going to do is construct those angles sticking off of the other side of that line segment. So whatever angle alpha is, I will just build it off of the line segment there. And whatever angle beta is, I'll do the same thing over here. And now I will just extend those lines until they cross our horizontal line, like so. Now you are probably thinking, where is he going with all this? I thought we were trying to establish an identity for sine of alpha plus beta. That's exactly what we're going to do. This weird construction puts the angle alpha plus beta into our picture. That's interesting. But how could that help us? Well, that is where this area formula is going to make a surprise appearance, because I've got this angle alpha plus beta. Do I know the sides surrounding it in this large triangle? Certainly I can figure them out, because of my two right triangles right here. They are both determined by angle side angle. Or on this one, angle side angle. So that means I could always call on SOHCAHTOA to figure out what these two sides are. But in fact, if I remember my other SOHCAHTOA shortcut, not the one where we know the hypotenuse and an acute angle, but where we know a leg of the right triangle and the acute angle adjacent to it, then we can do this even more quickly. Do you remember that second shortcut formula? It tells you that the other leg, the one opposite the angle, is the given leg times the tangent of the angle, and that the hypotenuse is the given leg times the secant of that angle. So this guy right here would be 1 times the secant of alpha. So plain old secant alpha. And similarly over here, the hypotenuse of this second right triangle would be 1, that leg, times the secant of beta. So plain old secant beta. And again, if you didn't remember that second SOHCAHTOA shortcut or never learned it, no big deal. Just pray to SOHCAHTOA, call on his name, and you will find these sides just as easily. Why does this help us? And again, I want you to appreciate this as a work of art, not as something you should be able to come up with on your own. Believe me, I would not have come up with this on my own either. So let's appreciate the brilliance of whoever did come up with this argument together. We are trying to come up with another expression for sine of alpha plus beta. We have concocted this picture that includes the angle alpha plus beta. And now we've done it in such a way that it's an angle in a triangle and we know the surrounding sides. That means by this somewhat obscure area formula, I can come up with an expression expression for the area of this triangle that will involve the expression I'm interested in, sine of the quantity alpha plus beta. Now the hope is, and we've mentioned this kind of thing before in earlier videos, the hope is that we can come up with another way, a second way of expressing the area of this triangle. So then we will have two different expressions for the same thing, this triangle's area. One of those expressions will involve the thing we want. We know that the two expressions will be equal because they literally will represent the same thing. So we will have an equation where one side involves the thing we want. Then we should just be able to solve for that thing we want, and we will have it. That's the overview from 10,000 feet. Now let's try to put this into practice. What we want to do is compute the area of our triangle in two different ways. The first way is going to be by using the SAS area formula directly. When we do that, we know that the area is going to be half the product of any two sides, so that'll be secant alpha, secant beta, times the sine of their included angle, which is alpha plus beta. So times the sine of alpha plus beta. That's the thing we want. So we're very happy to see that in one of our two expressions for the area of this triangle. Okay, the second way we are going to compute the area of our big triangle is to use the side angle side area formula again, but this time we'll use it twice. Instead of using it directly on the large triangle to get the area, we'll use it on the right triangle on the left, and then we'll use it on the right triangle on the right. We'll get each of their areas separately, and then we will add them together, and that will give us the area of the full triangle. So when we do that, what do we get? Well, when we use it on the triangle on the left, we get half the product of two sides. Well, that'll be 1 and secant alpha. So that just gives us secant alpha. And we have to include the sine of the angle between those sides, which is just plain old alpha. So we get sine alpha. Okay, so that's the area of that triangle on the left. But we have to add to that the area of the triangle on the right. And if we get that using the side angle side area formula, we get half of secant beta, which is the product of the two sides, times the sine of just plain old beta, the angle between them. All right, so this is great news because we now have two expressions for the same geometrical quantity, area of that triangle. And since these two expressions represent the same thing, they are equal. So what do we know? This expression, half secant alpha secant beta sine of the quantity alpha plus beta, is equal to this other expression, half secant alpha sine alpha plus half secant beta sine beta. This is great because now we have an equation, not just an expression, but an actual equation involving the thing that we want. So that means we should just be able to solve for it. Well, I have run out of room, so I'm just going to do this as much as I can as an exercise in stop motion animation. I want to solve for that. Let's begin by noticing that I have a half in all of these different places. We can get rid of those by multiplying both sides of the equation by 2. When I do that, this equation will turn into this one, where the halves are all gone. That's nicer already. Now, I'm trying to isolate sine of alpha plus beta on one side. So let's just divide both sides by secant alpha, secant beta. When I do that, we get this. Hey, that's nice. I now have an expression for sine of alpha plus beta. And no doubt you are thinking, oh my God, that is the goriest looking thing I've ever seen. I will never remember that. Well, I have good news for you. You don't have to remember that because this cleans up quite a bit. Look at this fraction on the left. We've got secant alpha upstairs as a factor and secant alpha downstairs as a factor. So of course they cancel out. And similarly in this second term, I have secant beta as a factor upstairs and secant beta as a factor downstairs. So they too cancel out. Seeing this should make your heart rate come down a little bit, but we can still make this nicer. Nobody really likes secants, but these can be cleaned up a lot. Because look, sine alpha over secant b, well that's the same thing as sine alpha times 1 over secant b. Well, the reciprocal of secant, what's that? Everybody knows the reciprocal pairs. Secant is cosine's reciprocal, and so of course the reciprocal of secant is cosine of beta. And similarly over here, sine of beta divided by secant alpha. Well, dividing by secant is the same thing as multiplying by cosine. So instead of dividing by secant alpha, we can write that as sine beta times cosine of alpha. And now we have an expression that is nice and clean and fairly easy to remember. I will record it up here in a moment, but I just want you to appreciate the artistry with which we have just seen this famous formula derived. Who would have ever thought that we could get to an identity for sine of alpha plus beta with an argument involving the area of triangles? This statement down here really doesn't have anything to do with area, but nonetheless, we used something about area to come up with it. There are other ways to derive it as well, but I think this is by far the most clever. So, I hope you enjoyed it. As I said, this is a pretty easy one to remember. The sine of the sum of two things is just the sine of one of them times the cosine of the other, plus, again, a sine and a cosine, but the positions are switched. For a quick example of putting this thing to use, let's come up with the exact value of the sine of 105 degrees. And you might be thinking, exact value? We can only come up with the exact values of trig functions at multiples of 30 degrees or 45 degrees. And this isn't either of those. Isn't this hopeless? It's not, thanks to our sum identity for sine, because we can recognize that 105 degrees is 60 plus 45 degrees, but now I could use that sum identity and take this sine of a sum and re-express it as, well, what's it going to be? The sine of one, so sine of 60 degrees, times the cosine of the other, plus the sine of the other times the cosine of the first one. And all four of these pieces are things we know exactly. So that means we can get this exactly. Sine of 60 degrees is root 3 over 2. Cosine of 45 is root 2 over 2. Of course, it's also 1 over root 2, but this is a much nicer form because it will play nicely with this other factor. So thinking ahead, this is the one we want to use. Anyway, sine of 45, root 2 over 2, cosine of 60. Remember your cofunction identity. That's sine of 30, so that's going to be 1/2. Do the arithmetic, and let's see, this is going to be a fraction over 4. It's going to be root 6 plus root 2 over 4. And that, my friends, is the exact value of sine of 105 degrees. It's a nice feeling to come up with an exact expression. Anyway, you can play some similar games like that in the homework exercises. And again, of course, no one in their right mind should memorize the fact that sine 105 is this. It's just interesting that we can come up with an exact expression for it. And you definitely should know how you can do it. As I said, this is a pretty easy formula to remember, so learn it. I should say, there is one objection one might make to our derivation of this thing. It worked beautifully so long as we could construct a picture like this. And for the size of the angle alpha I have here and angle beta, everything was fine. We could make beta a little smaller, we can make beta bigger, we can make alpha bigger, we can make alpha smaller, but there is a limit. This kind of picture only holds if what? Well, first of all, alpha and beta both have to be acute, because sure, beta could be 89.9 degrees and this would meet, way down the road. But if beta was, say, 100 degrees, well, forget it. That line would never cross this horizontal line, so we would never get a picture like that. Uh-oh, this is supposed to hold for all alpha and beta. This objection seems to point out that I've only proved that it holds for certain values of alpha and beta, for certain ranges. And the proof is immensely clever and works beautifully so long as alpha and beta remain in those ranges. But what happens when we get outside of it? Well, fear not. The proof can be extended to truly hold for all alpha and beta. Even if alpha is 9,014 degrees and beta is negative 224 degrees. I describe how this is done in the book. It's a clever argument in its own right, and it too makes lots of use of some of those on-the-fly type identities. So it's good practice to go through it, and I have one homework problem about that as well. But I'm going to take that as read here, because we do not have an infinite amount of time on our hands. So here is the sum identity for sine. Is there also a sum identity for cosine? An expansion of cosine of alpha plus beta? Well, yes, there is. I will go through the derivation maybe a little more quickly here than our derivation of the sum identity for sine. It uses the same old mathematical trick of computing the same thing in two different ways so as to get an equation that involves the thing we want, and then we can solve for that thing. So again, we'll get to the result in a second. For now, please try to enjoy this little work of art. Start with the unit circle. From the radius along the positive x-axis, rotate counterclockwise by alpha. From that same radius on the positive x-axis, rotate counterclockwise by beta. Take those 2 points and join them with a line segment. We are going to compute the length of this line segment in 2 different ways. The first way is just with the familiar distance formula. If we have 2 points and we know their coordinates, of course we can compute the distance of the line segment that joins them. Do we know the coordinates of these points? We sure do. By definition, since we've rotated this thing through alpha, the coordinates of that point are cosine alpha, sine alpha, right? That's how we define cosine and sine on the unit circle. And this is the unit circle. I'll put 1s on those radii. And how about this point? What are its coordinates going to be? Well, we've rotated through beta, but we've gone clockwise. So the coordinates at that point would be cosine minus beta and sine minus beta. But hey, we know some identities that are useful here. Cosine is an even function, so it absorbs that negative. Cosine minus beta can be simplified to cosine beta. And sine is an odd function, so that negative gets pulled through the sine. And instead of sine minus beta, we can rewrite that as minus sine of beta. That's a bit nicer. And let's call that line segment, or its length, how about d for distance? And since we know the coordinates of its endpoints, we can use the distance formula to find d. We'll do that in a moment. Or at least we'll come up with an expression for d in terms of all this junk. But there's another way we can get an expression for d. D is one side of this triangle right here. And to that triangle, I can apply the law of cosines. The law of cosines relates the 3 sides of a triangle and the angle of our choice. Ah! That's going to sneak cosine alpha plus beta into the picture. Clever, clever, clever. So we're going to compute d 2 ways. First way is with the distance formula, which we met back in, I think, chapter 4. You remember how it works. The distance is going to be the square root of the sum of the squares of the change in x and the change in y. And this, you will recall, just comes from the Pythagorean theorem. So what's that going to be here? Well, as we go from this point to this point, what is the change in x? We are going from cosine beta to cosine alpha, so that would be their difference, cosine alpha minus cosine beta squared. And for the y coordinate, so that's going to be sine alpha minus sine beta, so plus sine beta. And all of that is squared. Okay, that's our first fairly ghastly looking expression for d. Our second one is going to come from the law of cosines applied to the triangle I'm shading in right now. What does law of cosines tell us? Well, it tells us something about d squared. The law of cosines gives us the square of any triangle is, remember, it begins like the Pythagorean theorem, which it generalizes, the sum of the squares on the other sides. Well, so that's going to be 1 squared plus 1 squared, which of course is 2, but then we have to subtract off that little error term or correction term to account for the fact that the angle opposite d is not a right angle. And what is that correction term? You should remember it's twice the product of those sides. Well, that's 1 times 1, so 2 times 1 is still 2, times the cosine of the angle in between them. So that's where I'm going to pick up the cosine of alpha plus beta, which is the thing I want. So now I'm very happy. And you might say, well, don't get too happy. This is actually an expression for d, and this one is an expression for d squared. Well, that's no big deal. We can turn this into an expression for d by taking square roots of both sides. Great. So now I have 2 expressions for d, and one of them involves the thing I want. Those 2 expressions must be equal because they represent the same thing, the length of side d. So I am going to set up an equation where those 2 are set equal to one another. Terrific. Now we are in the home stretch because all the cleverness is done. Now it's just sheer manipulation, just a matter of turning the crank. But we do have to turn it skillfully. So we have this strange looking equation. We want to solve for the stuff in yellow, cosine of alpha plus beta. How are we going to do it? Well, of course, square both sides to get rid of those pesky square roots. And here is where a little foresight helps. Look at this stuff on the left. If I expand out this first term, that binomial, I know I'm going to get cosine squared alpha and a cosine squared beta and some other stuff, minus 2 cosine alpha, cosine beta. But important thing is I'm going to get a cosine squared alpha and a cosine squared beta. When I expand this one out, I'm going to get a sine squared alpha and a sine squared beta. Hey, that means I'm getting a cosine squared alpha over here and a sine squared alpha over here. They're going to combine, and thanks to the Pythagorean identity, give me 1. And the same story over here. So this left-hand side, I should be able to simplify considerably. And again, this comes from taking a moment to think about the equation before we just start hammering away at it. And it comes from knowing those identities, the Pythagorean identity, but also just the algebraic identity, that when I square a binomial, I get the squares of the individual terms and then a third term as well. So knowing all that, let's write this out. That left-hand side is going to become cosine squared alpha plus cosine squared beta minus 2 cosine alpha cosine beta. That's the first piece. And then the second piece will become all this stuff, sine squared alpha plus sine squared beta plus twice sine alpha sine beta. And the right-hand side just comes down. I'm just going to leave a equals right-hand side for now to save space. Because again, I'm going to make use of some convenient stop motion animation to save time. I've got cosine squared alpha and sine squared alpha. By the magic of Pythagoras, I know their sum is going to be 1. And then I've got cosine squared beta plus sine squared beta. By the Pythagorean identity, their sum is going to be 1. Put those ones together and I get 2. Now move this stuff over so that I have room to actually fill in the right-hand side. Hey, do you see what I see? I've got a 2 over here and another one over here. So if I subtract 2 from both sides, that's gone and that's gone. Oh, in fact, it looks like both sides have a factor of 2 as well. In fact, let's divide both sides not just by 2, but by minus 2, because that will leave me with just the thing I want on one side of the equation. When I do that, I get what I want on the right-hand side. The minus 2 disappears here, and this plus 2 becomes minus 1. And I've got it. Here is an expression for cosine of alpha plus beta. Let me go ahead and record it in the spot I originally made for it. Now, a couple thoughts about it. First, the objections that I mentioned could have been made about our derivation of the sum formula for sine could also be made for the sum formula for cosine because of this picture right here, which seems to only apply when alpha and beta are in a certain range. But once again, the argument can be extended using the same kind of ideas that we can use to extend this one. So if you're interested in that, please do read about it in the book. We don't have time to talk about that here. Suffice it to say that this too holds for all values of alpha and beta. This one is also pretty easy to remember. Cosine of the sum of two things, well, we get the product of the cosines of both things, and then we have to subtract the product of their sines. So you do have to remember that the plus goes with a minus. That's the one thing that's a little tricky to hold on to. But repeat it to yourself as many times as necessary when you're waking up in the morning, when you're taking a shower, when you're walking your dog, whatever. Get them in your head. They're not the most important identities in the world, but they're good ones to know. They do come up, and your teachers in future courses will be impressed if you remember them, because many of your peers will have forgotten them. But get them in there once at least. If you don't know it, let it be a case of honestly forgetting it after having learned it. There's a big difference between having learned something well once and then forgetting it and never having learned it well for the first time. If you never learned it well for the first time, it might as well have never happened. If you learned it well the first time, then it's pretty easy to get it back when the time comes when you find out that you need it. But that's it for these sum identities. It is time to move on to the double angle identities. We have a double angle identity for sine and cosine, and all these things do is give us a way to expand the expression sine of 2 theta or cosine of 2 theta. Each one of these expressions can be rewritten in a manner that does not involve 2 theta, and which is sometimes more convenient. What are these expressions? I hear you cry. Well, let's derive them. And unlike these, which required a lot of work and a lot of cleverness to derive, these are extremely easy to come up with once we know the sum identities. They're so easy I don't even need to clear out any extra space here. This tiny bit of space at the bottom will more than suffice. So let's start with the double angle identity for sine. Sine of 2 theta. Well, the reason this is so easy is because I can just write 2 theta itself as theta plus theta. So the sine of 2 theta is the sine of a sum, and I know how to deal with the sine of a sum already. Let's remember how it works. The sine of a sum is the sine of the first term, theta, times the cosine of the second term, also theta, plus another product of sine and cosine where we switch the two inputs. But switching them doesn't change anything here because they are both theta. So that was by the sum identity for sine. But of course, this simplifies greatly. In fact, I just have 2 copies of sine theta, cosine theta, and that's it. Let's put this in its preordained spot. Sine of 2 theta is 2 sine theta, cosine theta. And as I say in the book, this one just rolls off the tip of the tongue because it sounds like a line of poetry. It just bounces along. 2 sine theta, cosine theta. So this is a very easy identity to remember. And make sure you get it in your memory because it gets a lot of use in calculus. Excellent. Well, let's move on to the double angle identity for cosine, which I'll bet you could derive without any help from me at this point. But you're not in the room with me, so I'm going to go ahead and do it. This first step is where all the action is. We take 2 theta, the argument of cosine, and rewrite it as a sum, so that we can use the sum identity for cosine. And when we do that, we expand this out, and let's remember how the sum identity for cosine works. The cosine of a sum is the product of the cosines minus the product of the sines. So here that's going to be cosine theta, because that first one is theta, times cosine theta. The second one is theta, minus sine theta times sine theta. And that is by the sum identity for cosine. And of course we would clean that up in the usual way. That's cosine squared theta, and similarly we get sine squared theta. And just like that, in a matter of seconds, we have it. Cosine of 2 theta is the same thing as cosine squared theta minus sine squared theta. A very nice example of how identities beget identities. And these double angle identities should be firmly committed to memory. You should also have the sum identities memorized. But if you have forgotten them, your calculus teacher will forgive you, times being what they are. But the double angle identities really are crucial. They get used all the time, especially when you get to integral calculus. And since you don't know calculus yet, it's a little hard to explain how it would arise, but still, you'll end up with expressions like this. Oh my lord, what is that mystic symbol? That is an integral sign. You will learn about it in a future class. But anyway, something like this, never mind what it means, is hard to deal with as is. However, if you know your double angle identities, when you see this, you will have a quick reflex reaction and say, oh, I could rewrite that, if it's helpful, as 2 sine x cosine x, that poetic sounding expansion, times, of course, my original cosine x. And then I've got 2 copies of cosine, so I could put them together. And then, once you've learned a little integral calculus, you will look at this and say, ah, I know how to deal with that. That's something I can handle with ease. So as I say, never mind what any of this means for now. I'm just showing you the kind of place where it comes up, where being able to go back and forth between these 2 expressions is helpful. And it needs to be in your brain so that when you see something like this, you instinctively think, well, that's also 2 sine x cosine x. In the same way that already when you see something like the square of a plus b, you should at this point automatically think of that as being this as well. On any given occasion, this might be a more useful expression, or this one might be a more useful expression. Just like sometimes 1 over square root of 2 is more convenient to use, and sometimes root 2 over 2 is more convenient to use. So these trig identities you're meeting, they're like algebraic identities, they're like dealing with fractions which have multiple representations, and so on. They just give us different ways of thinking about the same thing. And you never know when one of those ways will be more convenient than the other. By the way, if the double angle identity for sine is easy to remember because it sounds like a line of poetry, the double angle identity for cosine is easy to remember because it looks so much like one side of the Pythagorean identity. We just have a minus there instead. Cosine squared minus sine squared is what we get when we expand out cosine to theta. And that little observation that this kind of looks like something in the Pythagorean identity will help us develop some further identities, which I don't even have in the book, but I'll show you here just to continue on in the spirit of identities begetting identities. This next set are identities that I call square killer identities, and they too are very useful in calculus. Their job, as their name suggests, is to kill squares. If we have something like sine squared theta or cosine squared theta, we will have identities that get rid of the squares. And to derive them, all we have to do is to observe that we already know 2 different identities that involve, say, cosine squared of theta. We're staring at one of them, the double angle identity for cosine, and the other is the one that this reminds us of, the Pythagorean identity. Let's just write them both down. Here's the Pythagorean identity, cosine squared plus sine squared is 1, and here's the double angle identity for cosine, where I've swapped the 2 sides to line up the matching or almost matching parts of our identities. Now here's a nice trick. Suppose we were to take those 2 identities and add corresponding sides of the equations. What would make us think to do that? Well, if we add them, these sine squareds are going to cancel each other out, while these cosine squareds are going to reinforce one another. So we'll end up on the left-hand side with 2 copies of cosine squared, whereas on the right-hand side, when we add those, we just just get 1 plus cosine 2 theta. And now, if we just divide both sides by this 2, we end up with cosine squared theta. Hey, that's what we were looking for, is this stuff. And lo and behold, there are no squares therein. So let's pack that into the spot we've left open for it. Easy. And you might say, hey, cosine 2 theta, double angle. I'm going to replace that by cosine squared minus sine squared. Well, don't do that, because then you'll get squares back. The whole point of the square killer identity is to get rid of squares. It's not that one side of any of these identities is better than the other. It's just that under certain circumstances, one side may be more useful, especially in contexts such as doing integrals in calculus. And you can get the square killer identity for sine squared using these exact same equations. Because if instead of adding them, I had subtracted, well, that will knock out the cosine squareds while reinforcing the sine squareds, because I'll get sine squared minus sine squared. So I'd end up with 2 sine squared on the left-hand side and 1 minus cosine 2 theta on the right-hand side. And now, of course, if we divide both sides by 2, we end up with our other square killer identity. So let's put it in its place. Now, there is no reason why you should memorize the square killer identities at this point. I just wanted to show you this, as I said, another example of identities begetting identities. And when you get to calculus and you are faced with something like integrating sine squared x, your teacher is going to show you these identities, and he or she will, I hope, show you where they come from too, and remind you that even if you ever forget these, you can always recover them very quickly, exactly as we did it here, by writing down 2 identities that everybody knows and then adding or subtracting. But you need to make sure that you are included in everybody. Yes, of course you know the Pythagorean identity, but you need to know this double angle identity for cosine as well, and the one for sine. By the by, these are not usually called square killer identities. They tend to be called either power reduction identities, which is like a bureaucratic way of saying square killer, and less exact for that matter, because you're not reducing powers. You're reducing a single power. Squares. That's what you're getting rid of here. But that's one name I've seen them go by. The other name I've heard them called are half-angle identities. That's actually how I originally learned them when I was a student. That was what my teachers called them. But it's sort of an awkward name because there aren't really any half-angles in here. Like you would expect things like theta over 2 in a half-angle identity, the way that in a double-angle identity, you get 2 theta. Now, you can turn these into something that involves the angle divided by 2, so it's not a crazy name. These are equivalent to what we might realistically call half-angle identities, but it's not exactly the most intuitive name. So if you use square killer identity, nobody is going to know what the hell you mean unless they took a class from me or read my book. So just bear that in mind. Feel free to pass the name on. It's a better name, but most people are going to say half-angle identity or power reduction identity. I did mention, though, that these can be massaged into the form of what are more genuinely understood as half-angle identities. So let me go ahead and do that for you as well. Again, this is just a matter of playing around. You need not memorize these for this particular class. You need not memorize the ones that are going to appear here. In fact, I do not know the ones that are going to appear right here off the top of my head. Anytime I need them, which is infrequently, I just start with these square killers, which I do know, and take 2 seconds and derive them from them. So here's how it works. A half-angle identity. I expect this to be an identity involving something like the sine of theta over 2, the sine of x over 2, the sine of alpha over 2, whatever. The sine of some input over 2. Well, I can get that from this square killer identity in 2 quick steps. First, let's literally get rid of that square by taking the square root of both sides. If I do that, then I would have plain old sine theta is plus or minus the square root of 1 minus cosine of 2 theta over 2. Now, let me just make a substitution. Instead of theta, let me substitute alpha over 2. Well, if I do that, I have to do the same thing over here. And for this theta, substitute alpha over 2. But then I would have alpha over 2 times 2, which would just give me alpha. Aha! Now look, now I have an identity that with a straight face and my head held high, I'm willing to call a half-angle identity for sine, because it's sine of half of an angle. So if I write that down, I'll have this stuff. And of course, I could do the exact same thing to get an identity for cosine of alpha over 2. How would I do it? I would start with my square killer, take square roots of both sides, and then in place of theta, put alpha over 2. So I would end up on the right side with almost the exact same thing, except I have a plus where I had a minus before. Good. And there are further and further identities we could develop, but I'm probably trying your patience already. What I want you to see from this is that the sum identities are powerful because once we have them, all sorts of other identities start rolling out of them. These ones are very useful in calculus, much less so for the half-angle identities, although they have their charms too. And I'll show you, maybe to finish this video off, something we could do with these obscure-looking identities. Okay, remember when we used the sum identities to come up with exact values of sine and cosine of 105 degrees? Well, I can do something similar with the half-angle identities. We could come up with some more exact values. But I want to show you an interesting pattern that develops when we do that in just the right way. So let me start just by making a table of some angles and exact expressions for those angles sine and cosine. And let's start with something we know, pi over 4. Well, of course, everybody knows the sine is root 2 over 2 and the cosine is root 2 over 2 as well. Fine. But suppose we move on to pi over 8. Pi over 8. Well, if that's pi over 4, that's pi over 8, 22.5 degrees. Just think straight in radians. It's eighth of a half turn. What are the exact values of sine and cosine pi over 8? How are we going to figure that out? Well, obviously, we're going to use these half-angle identities. That's why I left them up in the corner here. So let's start with the sine. We are interested in the sine of pi over 8. But pi over 8 is, of course, half of pi over 4. And, as luck would have it, we happen to know a half-angle identity for sine. So the sine of half of pi over 4, according to this formula, is this stuff, plus or minus the square root of 1 minus cosine of the thing upstairs, which is pi over 4. Ah, we know that, over 2. Oh, and truth be told, we don't need a plus or minus in this particular case because we know we are looking for sine of pi over 8. Think about the unit circle. Pi over 8 lives somewhere over here. Clearly, the sine of pi over 8 is positive because the y-coordinate at that point is positive. So I'll just get rid of that plus or minus. Anyway, this is something we can just bash out because we know that the cosine of pi over 4 is, as we already recorded in our table, root 2 over 2. Now please, simplify that. I sometimes have students in courses like this, or even beyond, who are intimidated by things like this. Don't be. You can simplify this. Just crunch the top into one fraction, divide by 2, that'll be one fraction, and then you'll have the square root of an ordinary fraction, rather than fractions within fractions. So anyway, how do we do that? Upstairs, we have a common denominator of 2, so we will have 2 minus root 2 over 2, all of that over 2, and when you divide a fraction by 2, it's the same as multiplying it by a half, which means that all of that will just be over 4. Ah, and the square root of a quotient is the quotient of the square roots, and the square root of 4 is 2, and that's much nicer than that ugly thing up there. So let's go ahead and put it in our table. Okay, so the sine of pi over 8 is exactly this interesting expression. And of course, we could do the same thing to get the cosine of pi over 8. So we write that down, then evaluate cosine pi over 4. Then we go through the usual arithmetic contortions to obtain our reduced answer. So let's bring that one home. And there it is. So now we have exact values of sine and cosine at pi over 8. Now, if we keep going by cutting that angle in half and looking at pi over 16, of course, we can proceed in the same way because now we know how to deal with the sine and cosine of pi over 8, so that when cosine of pi over 8 appears in our expansion, we can evaluate it. And again, this should pose no problem for anyone to simplify. It's just applying the basic rules of arithmetic. And before you know it, here we are. And I'm not going to write out the details of cosine of pi over 16, but it's going to turn out to be, as you can verify, this stuff. And I just want you to notice the pattern that's developing here on the cosine side. We started with root 2 over 2 at pi over 4. And when we halved our angle, well, we had to ram an extra plus square root of 2 under the existing radical. Then when we halved our angle again to pi over 16, we rammed yet another plus square root of 2 under the innermost radical of our last expression. Well, can you guess what the cosine of pi over 32 is going to be? I'll bet you can. It's going to be this bit of nested nastiness. But it's not that nasty. It's actually quite pretty. It's built of nothing but 2's. And that pattern continues forever. You can play around with that more if you want to on your own to confirm that. But as a final flourish, as we are drifting far away from trigonometry just into playing around with interesting mathematical ideas as they arise, let's just think about those numerators that we're getting. Imagine not just 1 square root of 2, or nested 2 deep like that, or 3 or 4, but if we kept going forever, nesting those radicals infinitely deep. So is it possible to make any sense out of that sort of thing at all? When you get to calculus, you'll study infinite sums, but infinitely nested radicals is a very strange idea. You could play around with this numerically on a calculator and, figure out an approximation to what that numerator is down there, where you have the thing nested 4 deep, and then do it 5 deep, and 6 deep, and 7 deep, and see what's happening. But I claim that we could actually figure out an exact expression for this thing without monkeying around with calculators at all. I actually have a whole video on this topic that I'll put a link to in the notes. But very quickly, here's the idea. Whatever this strange object is, let's give it a name. Let's call it x. Now I'm going to rewrite it in a very clever way. I'm going to rewrite it as the square root of 2 plus, well, what is all of the stuff that's left over? What's left over is an infinitely nested set of square roots of 2. Hey, what's left over is, strange to say, x. So yes, this object actually contains itself many times over, in fact, but we can just say that x is clearly equal to the square root of the quantity 2 plus x. Well, that's good news, because if I square both sides, I can get rid of the radical, and then I can push everything over to one side of the equation, and hey, that factors. So that tells me that x must either be 2 or minus 1. What? This thing? Well, clearly it can't be minus 1, because everything in here is positive, so we can get rid of that. And we are left with the strange conclusion that x, this weird expression, is in fact equal to just good old-fashioned 2. How can that be? Is there some sort of mistake? No, it's correct. And actually, come to think of it, we can use some trigonometry as a kind of sanity check to help us accept that this is fairly intuitive. Think about the table we were developing here. If we kept going and looked at pi over 64 and pi over 128 and so on and so forth, these would be developing the same way with more and more nested square roots. So what is the limit towards which this is all tending? Think about the angles. We started with pi over 4, then we cut it in half to pi over 8. Cut that in half to pi over 16, cut that in half, pi over 32, cut that in half to pi over 64, and I'm running into the limits of what I can show you without blowing this up even more. But what's happening to these angles? They're getting closer and closer to 0, right? An angle of 0. And as we do that, what's happening to the cosines? Well, they're going to follow that pattern, and they are going to get closer and closer to that crazy infinite expression over 2. But I claimed that this crazy infinite expression is actually equal to 2. Well, if that's so, that means this must be getting closer and closer to 2 over 2, which of course is 1. Does that make sense? Well, this would be the cosine of 0. And what is the cosine of 0? Of course, the cosine of 0 is 1. So yes, this actually fits the pattern of what we were seeing here trigonometrically perfectly. And that is a very good place to end this video. So I'll see you next time when we talk about inverse trig functions. Until then, goodbye.